how do computers do calculations, sort of what's inside a computer, and a little bit about why they do it that way. So to start, we know that computers operate using what is known as digital signals. So digital signals either have a value of 0 or a value of 1, and they're used to encode information in terms of on and off. So as simple examples, you can think of digital signals in terms of numbers. So every string of binary or digital signals will make up some number that you're more familiar with. And that sort of conversion is just a conversion between different bases in math. So you can count in base 10, which is what we do as humans. And there's questions as to why we use 10. My personal thing is that it's the number of fingers we have on our hands. But then computers, they use base 2. So everything is either on or off, and you just count how many different on and off and which parts of the digits or the binary digits are on or off. So the way that the computers utilize this on and off information really boils down to the way that transistors work and the way that you can form digital logic from transistors. So there's sort of the thing that people are really comfortable with. Like, you're comfortable using the computer and the software and the display and so forth. But in order for the computer to work and carry out what you want to do with it, it needs to translate your commands and your inputs into binary so that the computer can do processing on it. So there are a bunch of different layers in terms of talking about how do computers work. There's sort of the user interface, which is sort of like the most abstracted, the most user-friendly type level, where you're used to having input devices like a keyboard and a mouse. And then there's the software, which is the layer directly underneath it. And the software is what's converting sort of your inputs and your outputs back and forth into computer language. Now, the computer language then goes down another level, and there's something called machine language. And machine language is the instructions that are given to the computer to be able to work. Now, in order for that to be realized, there has to be hardware. Then the hardware is what's actually doing the processing of information. So there's input that you're giving it in terms of what you're typing into your keyboard, what you're moving in your mouse. Maybe you're doing some calculation, or maybe there's some image that the computer is processing. So it needs to convert that to machine level instructions that it can give to the chips that are in the hardware. And the hardware is what is acting on your commands in order to carry out the calculation, or to display, or to process whatever information it's receiving. Within the hardware, there's a bunch of different functionalities. So usually you think about the different functionalities in terms of the memory aspects, in terms of the central processing, and in terms of the communication. So there's central processing units that are doing calculations. They store results either in temporary memory, like their RAM, or in permanent memory, like your hard drive. And there needs to be communications between these different parts of the hardware in order to realize the functionality. So what we're going to be doing today is we're going to really focus on the hardware as it pertains to digital logic. So in order for the computer to do various computations, to do comparisons, to do sorting and so forth, it works by operating with a set of fundamental rules. The fundamental rules are known as the Boolean logic rules. So they're just rules to decide if I have two numbers that are represented in binary, how do I interact these two inputs and produce an output? Now, at the end of the summer session, we talked about the 6 logic gates that are most common in, that you most commonly see in your design. So I forgot to mention that you should also have your textbook with you. So we're going to be looking at some of the activities in chapter 14 and also some in chapter 7. So let me first just start with page 142. So this shows the 6 standard 2 input, 1 output Boolean logic operations. And then there's also a single input, single output NOT operation. Now, we did some of these activities in software, and the goal for the first half or the first hour is to be able to realize these results using the hardware that was provided. So we want to see that the logic gates that we've provided do in fact produce the logic tables. That what we want to do first is to really talk about this blue circuit and sort of its functionality and why it's being used. So what we'll do, I'm going to ask you to also look at page 271, which is the, or sorry, 272. 272, which is the full LED calculator that we did with the summer camp students. So what you should see on page 272 of the text is that there are sort of lots of wires and lots of switches and lots of connections between the different gates. And the top image in that picture, and let me see if I can just share screen because that might be easier to go through. So. Okay, so what you should see is that this was a really neat example where one of the students meticulously cut wires to the correct length and put together their light emitting diode calculator in a really nice, clean format. So this is using the original approach that we did with the summer camps, where we had individual switches, we had individual LEDs and resistors. We had to power these elements and also power the switches. And then sort of a more typical circuit that the students would build looked a lot more like this. And it was really difficult to debug and help students to understand whether their circuit is working or not. Are they misconnecting some of the circuit diagrams and so forth? And so what we've done is we've abstracted away the input part of the circuit and the output part of the circuit. And we've created a separate chip. And the separate chip, the goal is to, number one, give firsthand, very simple experience doing soldering. But then the second is to abstract out a lot of this complicated hardware. So the final version of the LED calculator circuit, when you build it, is a lot neater. It's a lot fewer elements, a lot less wiring, and a lot easier to debug. So the goal for the end of today is to get into some of this building. Like, we may or may not fully get through building the LED calculator, but we want to understand how does it work. And in order to do that, we want to first talk about this blue circuit board.